Good morning, geometry scholars. We are starting a new chapter on circles. You know a lot about circles, but we're going to give you some specific vocabulary. We've got 2 theorems and 5 examples in this section. And we're also going to talk about some of the algebra skills that you need to review in order to talk about lines and segments that intersect circles. So our objectives are to identify special segments and lines, draw and identify common tangents, and use properties of tangents. And here we go. So we have some definitions of special points. You've probably already seen these before, but let's refresh. Identifying special segments. A circle is, the definition, the set of all points in a plane that are equidistant from a given point called the center of the circle. A circle with center P is called circle P and can be written as circle P with a little dot up in the middle of a circle. So that's the definition, all the points equidistant. The core concept is that lines and segments that intersect circles, a segment whose endpoints are the center, and any point on a circle is a radius. So basically a radius is from the center to any point on the outside. A chord is a segment whose endpoints are on a circle. And a diameter, here it's green, a diameter is all the way across, so it's blue. It's a chord containing the center of the circle. The word radius and diameter refer to lengths as well as segments. For a given circle, think of a radius and a diameter as segments and the radius and the diameter as lengths. Okay, so a radius and a diameter are segments, and the radius and the diameter are lengths. We also have what's called a secant, S-E-C-A-N-T, and a secant is a line that intersects a circle in 2 points, as you can see the green one here. A tangent is a line in the plane of a circle that intersects the circle in exactly 1 point. That's called the point of tangency. Here it's B. You can see it's red. The tangent ray, AB, and the tangent segment, AB, are also called tangents. So recall, the most important thing about a tangent is that it touches the circle in exactly 1 point. So we'll do an example here.
Tell whether the line, ray, or segment is best described as a radius, chord, diameter, secant, or tangent of circle C. Part A, segment AC. Part B, segment AB. Part C, ray DE. Part D, line AE. Solution. Part A. Locate segment AC in the diagram. Segment AC is a radius because point C is the center and point A is a point on the circle. Part B. Locate segment AB in the diagram. Segment AB is a diameter because it is a chord that contains the center C. Part C. Locate ray DE in the diagram. Ray DE is a tangent ray because it is contained in a line that intersects the circle in exactly 1 point. In this book, assume that all segments, rays, or lines that appear to be tangent to a circle are tangents. Part D. Locate line AE in the diagram. Line AE is a secant because it is a line that intersects the circle in 2 points.
So that first part, it's just identifying. Used to that vocabulary. These are examples we do in our class notes. And here's a way to draw them. We have some core concepts here. We have what's called coplanar circles and common tangents. And they're exactly what you would think they are. Coplanar is on the same plane, and common tangents means they touch both. But we'll read the definition. In a plane, 2 circles can intersect in 2 points, 1 point, or no points. Coplanar circles that intersect in 1 point are called tangent circles. You can see it here in red. Coplanar circles that have a common center are called concentric, and that's the green over here. A line or segment that is tangent to 2 coplanar circles is called a common tangent. A common internal tangent intersects the segment that joins the centers of the two circles. A common external tangent does not intersect the segment that joins the centers of the two circles. So this one would be exterior, this one would be interior, but it doesn't go through the blue part here. So we're going to do another example of the three types of intersection. Either they don't intersect at all, 0 points, they intersect in exactly 1 point, tangent, or they intersect in 2 points, as you can see in example C.
Tell how many common tangents the circles have and draw them. Use blue to indicate common external tangents and red to indicate common internal tangents. Solution. A line or segment that is tangent to two coplanar circles is called a common tangent. A common internal tangent intersects the segment that joins the centers of the two circles, and a common external tangent does not intersect the segment that joins the centers of the two circles. So first draw the segment that joins the centers of the two circles, then draw the common tangents. Use blue to indicate lines that do not intersect the segment joining the centers, and red to indicate lines that intersect the segment joining the centers. Part A. Draw the segment that joins the centers of the two circles. There are two common internal tangents and two common external tangents, so there are 4 common tangents. Part B. Draw the segment that joins the centers of the two circles. There is 1 common internal tangent and 2 common external tangents, so there are 3 common tangents. Part C. Draw the segment that joins the centers of the two circles. There is no common internal tangent, and there are 2 common external tangents, so there are 2 common tangents.
Hopefully, and if you don't get that, stop, rewind, watch again. Again, more examples in class together, and here are the theorems that I mentioned. So the first one is a tangent line to a circle theorem. In a plane, a line is tangent to a circle if and only if, remember that's bidirectional, it goes both ways, if the line is perpendicular to a radius of the circle at its endpoint on the circle. So you see the picture here. QP is perpendicular to that line. PM, line M, the blue line, is tangent to circle Q if and only if M is perpendicular to QP. That's the only way it works. So if you have a radius perpendicular to a line that connects, then you know you also have a tangent. The second theorem is an external tangent congruence theorem. Congruence. Tangent segments from a common external point are congruent. This is going to be super handy, so pay special attention to theorem 10.2, and this is how it's stated. If SR and ST are tangent segments, then SR is congruent to ST. And we're going to use that a lot. So example 3.
Is segment ST tangent to circle P? Solution. If segment ST is tangent to circle P, then segment ST is perpendicular to the radius PT at point T, which means triangle PTS is a right triangle. So use the converse of the Pythagorean theorem to show whether or not triangle PTS is a right triangle. Does 12 squared plus 35 squared equal 37 squared? Evaluate the powers. 12 squared is equal to 144, 35 squared is equal to 1,225, and 37 squared is equal to 1,369. Add 144 and 1,225, and you get 1,369 is equal to 1,369, which is a true statement. Because 12 squared plus 35 squared is equal to 37 squared, triangle PTS is a right triangle, and segment ST is perpendicular to segment PT. So segment ST is perpendicular to a radius of circle P at its endpoint on circle P. By the tangent line to circle theorem, segment ST is tangent to circle P.
Any questions, make sure you ask me in class. Here's another example of finding the radius of a circle.
In the diagram, point B is a point of tangency. Find the radius r of circle C. Solution. You know from the tangent line to circle theorem that segment AB is perpendicular to segment BC. So triangle ABC is a right triangle. You can use the Pythagorean theorem to find the length of the radius. By the Pythagorean theorem, AC squared is equal to BC squared plus AB squared. Using the information given in the diagram, substitute R plus 50 for AC, R for BC, and 80 for AB, which gives you the quantity R plus 50 squared is equal to R squared plus 80 squared. Multiply, and this gives you R squared plus 100R plus 2,500 is equal to R squared plus 6,400. Subtract R squared and 2,500 from each side of the equation, and this gives you 100R is equal to 3,900. Divide each side of the equation by 100, and R is equal to 39. So the radius is 39 feet.
Easy enough to follow. Be sure you multiply your binomials all the way out using our FOIL method so that you end up with a trinomial, and we will talk about that in class as well. There's going to be a lot of algebra in this chapter. One more example. We're not doing constructions while we're distance. Here's the example.
Segment RS is tangent to circle C at S, and segment RT is tangent to circle C at T. Find the value of x. Solution. The external tangent congruence theorem states tangent segments from a common external point are congruent. So this means RS is equal to RT. Using the information given in the diagram, substitute 28 for RS and 3x plus 4 for RT, which gives you the equation 28 is equal to 3x plus 4. Solve for x by subtracting 4 from each side of the equation, which gives 24 is equal to 3x, and then dividing each side of the equation by 3, and 8 is equal to x. So the value of x is 8.
That's it. That's all we have going for this section, and I'm pretty sure it's time to start your problems. Okay.